you everyone for joining. Today I'll be talking about the physiomechano model for pulmonary and COVID-related diseases, and this is with the aid of my professor, Jolo. So first, I start by defining the problem and the solution. What's going exactly in the lungs and why is this relevant? The research basically focuses on the alveoli. The alveoli is the smallest units in the respiratory system. And since they are so small, they are more vulnerable, meaning that any pulmonary disease symptoms will first arise in these tiny sacs of air. They also release surfactant, which keeps the alveoli from collapsing by reducing surface tension and surface tension present within the alveoli. So the presentation starts by, the research starts by hypothesizing that the lung diseases such as lung infections and the presence of excess fluids in the lungs and impaired gas exchange could be all linked to the lung surfactant release in the lungs. So research process. So where did this interest arise from? It arises from interest in COVID-19 and the physiological and biological responses. We all know that most deaths in COVID-19 happened from lung failure. So because of that, we hypothesized that if we can treat whatever is going on in these tiny sacs of air, then maybe we can figure out how to treat all these pulmonary diseases and how they're all linked through the surfactant. First, I started by doing a lot of research, and then I came up with solutions and a design process, and then fabrication testing and data analysis. And I end this presentation by what I've learned. So for the design process and design modeling, I had 9 different variations. If you look right here, this is the CAD drawing of the device. This right here is going to be the liquid inlet, and this right here is going to be the liquid outlet. And this right here is going to be the gas inlet where the gas would be flowing. So the device behaves in a liquid and gas manner. These right here, these sacs right here are the alveoli clusters. We have 4 of them. And I've did again, 100, 200, and 300 micrometer. The 100 had different number of pores. The 200 had also different number of pores, and the 300 also had different number of pores. So the one that we tested the most is the 200 one, which had 18 pores right here, since it's the middle ground for all the alveol designs. For fabrication and testing, we did photolithography, which basically is a process where light is used to transfer geometric pattern from a photomask to a photosensitive chemical photoresistant on the wafer. The device was then sandwiched between 2 alveolar sacs made from PDMS to form a sandwich. So there were like 3 layers. The middle layer, it contained the device. The outer layer, it contained an alveolar sac. And the other outer layer also contained an alveolar sac. That way, the device would be able to expand in a 3D manner, and the device would be able to sustain that expansion. And for testing, we first started by testing a clog device, which I thought it behaved in a really interesting manner. Again, the 200 micrometer one was tested. 2 phases were tested. The first testing had a series of only gas being flown in, and the 2 phase had both gas and liquid being flowed in. So here again is a zoomed in picture of the device. Right here would be where the liquid would be flowing. It would be flowing from this to this right here, and right here would be where the gas would be flowing. And these right here would be the pores, which model gas exchange between the liquid interface and the gas interface. So here are the results of our measurements. For the gas phase only, 4 different flow rates for the gas were tested: 5 SCCM, 10 SCCM, 30 SCCM, and 60 SCCM. And then the outer diameter, which is this one right here, versus the inner diameter, which is this one right here, were ratioed against each other. And obviously, with an increased flow rate, we have an increase in the diameter. But an interesting phenomena is it increasing to a certain point and then decreasing and leveling out, which kind of behaves like an actual alveoli, which is the whole point of this device. Again, we also tested the pore size percentage change between the one phase and the two phase measurements. For the two phase measurements, we used 55 SCCM. And again, obviously the pore sizes would decrease with an increase in the gas pressure and an increase in the water flow. Okay. And stability, okay, so again, the inner and outer diameter change in length and the stability within the gas and liquid flow. So the reason why I mentioned the clog device was because the results for that device were less stable than the results of a device that wasn't clogged, which kind of gives us a hint of, what happens when you have all these pulmonary diseases happening in your lungs and how it affects the overall turbulence and stability of the gas flow and the airflow. Conclusion and future possibilities. The device is still in its beginning stages and has a long way ahead. So there's still a lot of modifications that we need to do. One of them being that we need an actual gas outlet. We only have a gas inlet. And the other one would be having the device be more stable, since we did run through a lot of problems throughout the design process. And how exactly can we use this device? There are plenty of ways we can use this device. One of them being having actual alveolar cells in there that release surfactant, and measuring how the presence of the surfactant that is secreted in the alveoli and its absence affects the actual expansion and contraction of the lungs. And other and design modifications requires obviously more research and more testing. And that's pretty much it. Thank you so much for joining, everyone.